So it's 6 now. I will start in 2 minutes. Let's see anyone joins or not. Yeah, am I audible? Can you please just respond? Just you can just write in the chat if I am audible. Yeah, okay, fine. So, hello everyone, welcome to this tutorial for NPTEL course on reinforcement learning. My name is Vijay Mukherjee and I'll be your TA for this tutorial, and I'm a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. So we'll be solving mostly some tutorials. Yeah, am I audible now? Or I need to be louder a little bit more. Okay, I mean, I can hear myself also, like, clear. Okay, okay, fine. Yeah, so we'll be, first I will give you an overview of what was the course of this week, and then we will try to solve some problems which is quite similar to your assignments and all. So let's begin. So the previous week we were introduced to things like return, right? We are introduced to this term called return, which was basically GT is basically RT plus RT plus 1 plus dot 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 to a particular terminating state RT, right? This one was the thing return we discussed last time. So also another thing. So what was written? So this one, if this one is a this one is your task, or let's say states. So the total reward for future states, right? We are also introduced to the concept of Markov decision problem, MDPs. We discussed what is an MDP. Like you have an you have an agent, you have an environment, you have an agent and an environment. The agent the agent performs an action. So first agent senses what state it is. It performs an action according to it. Accordingly, it gets a reward corresponding to it, and as well as the state changes to S1 plus 1. S, if it was previously Si, so it is Si plus 1. So right. So this was probably the like the state and the action and everything that was discussed for an MDP. So for an MDP, what are the basic operators you have? So you have your like there is return and there was discounted return. Okay, so GT is equals to RT plus 1 plus gamma RT plus 2 plus dot dot dot, right? So there the discounted factor is how much confidence you have in your current return and how much confidence you have your future return. That was part of it. That was part of your that was part of your like discounted return factor. So discounted factor was alpha, which determined whether you okay, sorry for that. So discounted factor was there. So discounted factor give you a preference whether what preference you are giving to your future return or current return and all. So that was the part of your discounted return. And so our MDP problem can be of an RL can be given using this, can be described using these five parameters rather. Your discounted factor gamma, then your set of states, set of actions, and then state transition. So you have been given a state S and A. What is the probability that you reach the next state is S dash, and the estimation of reward. So what will be the reward R given S dash A S, meaning the new state is S dash, previous action was A, and the previous state was S. So also this one was one of the things like, so you are previously an SI, state I, and you take action I. Based on it, you get reward I, and your state becomes Si plus 1. Sorry, I plus 1. And so this was your classic MDP problem that was discussed last week. Also, you are introduced to the term called uh, value function. V pi of S, and action value function, right? So these are the two terms you are introduced to. So what was the pi? Pi is your specific policy corresponding to which we select the states and action. like it's basically a mapping, or a mapping of action to states, right? So these were there, all the parts that were discussed last week. So these two were the parameters that were there, and we haven't yet uh, discussed how to get these values, right? So one is your value function. So value function, as you know, so what is the future reward you will get at state is, currently when you are at state is, what is the expected reward, total return, sorry, not reward, return at state is, and q s of a, pi s of a, that is the action value function. So currently you are at state a, and the next action you are taking a. So based on that, how much value you will get. So last week I show you the chess problem, that how, what is the value function in the chess. So at a certain position, suppose ace, like at a certain position, that is the ace, there are few pieces on the board, you are playing as a with the white. So what is the value currently, so how close are you to your winning the game, was given by your value function. And if you play a certain move, so what is the value for that move, how, what will be the value you will, how close will be if you play a move, that was your action value function. So these are the things I discussed last week. So let's come now to what was discussed this week. So this week we derived the equations for these two terms, right? So first was your v pi s. So what is your v pi s? So by v pi s, you specifically mean that what is the value of like what is the expected return you get when you are at state s, right? So it is given by the, so it is given by the formula, empirically this estimation of pi gt given st is equals to s, right? So currently you are at state s. What is the expected return you expected return you are like you might get from this state, right? This is your v pi. So we gave so in the class it was shown how you derive the formula from this to what we call the Bellman equations. So I will directly write the Bellman equation. I will not go into details how to derive it, but so the Bellman equations is given by summation of a pi of a given s comma s dash, now s dash comma r, p of s dash comma r by a comma s multiplied by r plus gamma v pi s dash, where s dash equals to s of t plus 1, right? So how if you want to get into details how you are getting this equation, so I can give you a hint how we are getting it. So let me just give you a hint for this, how we are getting this. So let me write this again. So you have v pi s, which is the expected return at state s, that is gt expectation s of t is equals to s, right? Now since this is a return, we can write it recursively as r plus 1 plus gamma g of t plus 1 given s of t is equals to s, right? So we can write this. So if you have any doubt regarding this equation, you can say first if you have any doubt regarding this equation. So this part is clear, right? So how you are getting the so what is the value function at state s, which is basically the expected return from state s if you start from state s, right? So any doubt regarding it?
No doubts.
Okay, thank you. So so now what you can recursively write it down is this, right? Because expected return, and so what does this mean? This means is expected return at time t plus 1, at time t plus 1, right? Now so one thing you can see that expectation. So if you remember the equations for expectation, so expectation of a plus b is equals to expectation of a plus expectation of b. Okay, so in similar way we can divide this up. So this part can be called as expectation of r plus 1 given rt plus 1, rt plus 1 given st is equals to s plus e pi gamma gt plus 1 given st is equals to s, right? So using this using this linearity of expectation, we can just write it like this. So now it becomes two parts. So you have to derive it for this part. So you have to derive it for this part, and you have to derive it for this part. So if you look at the first term, expectation of reward at state S. What is the reward I am expecting at a state S? So from state S, what is the expectation I am expecting? A reward I am expecting. Right. So let's do it. So we can write this as, this expectation can be written as so one more equation I think will be very helpful for you to how to measure expectation. So suppose you are given this. So how to measure an expectation? So the measure of an expectation is basically this. A into sorry. So let me write it as x. So x belongs to a set of all values. It will be this. Right. So this is how you calculate an expectation. This is how you calculate an expectation. So similarly, we will do it same here. So this can be written as expectation, this term, that is the r, into probability of r t plus 1 given s of given s. So let's write down like this. Okay, so this will be the simplified form. Okay, so now let's expand this. Okay, So what is this? What does this say? So what is the probability that I will get? What is the probability? So these are sum of all the states. So this becomes to R belongs to a state of all rewards. R belongs to state of all rewards, right? So let me use the smaller notations. Okay. Uh, so let me use these notations. So this is saying that what is the probability I get the reward is at state is. So now we can write this as P of A comma S into P of R by S comma A. Right? We can write it like this. Why we can write it like this? Because this is a conditional probability. So uh, we can expand it like this. So what does this mean? That at state A, if I take action A, what is the reward I am getting at state S, and for state A, all the rewards we are like we are summing it up here. Okay. So this is how you expand this, and you will get this term. You will get this term, this term, and this term. Similarly, if you expand this will basically gamma over your v prime will come. So if you expand this, so this is how you derive the this equation, this v pi equation. Okay. So ultimately, it's you have to solve these equations one by one and do it. So if you want to go in deep into the derivation. Okay. So similarly you have your q value equation. So your q value equation will be something like this. Q of pi, you are at state S and select A. So it will be so it will become, so basically you are selecting a specific value of A here. So this one will go up, and it will ultimately be this summation S dash P of S dash comma A by R comma S R plus V star V prime S dash. So this is your action value function. Simply, what does this mean? That at state S, you are taking a particular action. So if you are taking a particular action, this value, this pi of SA will become 0, nothing more. Right. So this is how you derive your Bellman equations. So these are your Bellman equations. Equation for V pi is and Q pi is of A. Right. Now, what is specifically a policy? So policy is basically your, so so this is your let's say this is your value and this is your states. So basically policy is your a graph which calculates, suppose this is your graph, okay. So over all the states it will calculate all the values. So for all values there is, see, there is a particular state, right? For all state there is a particular value. This is your basically your policy. This is a graph which represents one of your policy, right? So this is a policy, a mapping from state to action, and for the corresponding value for each action can be drawn like this. So this is your policy. This is your one policy. Now our task, so if you remember our like bandit problems, so our task was always, so task of RL is always to select the most optimal policy. So what do you mean by optimal policy? So how are you comparing a policy? So we term a policy P1 is greater than policy P2 if for all states V pi 1 is greater than V pi 2 S. S belongs to let's say a capital S, all states, right? So so we are saying that P1 is better than P2 if like if there is a graph like this, let's say. So this is your suppose this is your pi 1. So this is your pi 1. Now let's say there is another curve exists like this. So you see in this curve, let's say pi 2, the pi 2, the value at each state is better than pi 1. The value at each state is better than pi 1 if you look at the graph. Okay, so that determines, that says that pi 2 is better than pi 1. Okay, now it is always so now the theory says that it is always tough to find an optimal solution like this, that there exists such a policy which is always greater than at each state it is better than every other policy. So I mean to say getting such a clear graph is very difficult. So in most cases, what you will be doing is something like this. So suppose you have this graph. So you have your states and you have your value. Okay, so let me draw a line. So this is your one policy, let's say pi 1, and this is your other policy, let's say pi 2. So what is special in the so what is the different from the curve we draw before? So in this curve, pi 2 is not greater than pi 1 at each state, right? So in some particular state it is better, in some particular state it is not, right? So your is in each state or expected value over the entire transaction gives better value. Is it each state? Is it each state or expected value over the entire transaction gives better value? No. So is it at each state? Yes. So if you think about optimal, so in optimal, So in optimal, our requirement is, so let's first evaluate the policies. Okay, so policy evaluation says that if pi 1 is better than pi 2, if for all values at each state, pi 1 gives a better value than pi 2. So by looking at the graph, you can see that pi 2 is giving a better value than pi 1. So in this case, pi 2 is greater than pi 1, right? So in that case, I can say that pi 2 is better, is a better value function than pi 1. But you will not always get such a curve, right? That's what I mean to visualize you. So does this answer your question? It is at each state the expected value should be the highest. That is our goal. So that is what we want to find. Okay, so let's come back to this graph which was drawing. So now you look at this, there are two policies. So one policy is doing better. So if you see policy 1, policy P1 is doing better for these states. Pi 1 better. But for these states, pi 2 is better. So if you want to find an optimal policy in this case, we have to do a third policy. We have to say that that the optimal policy is neither of pi 1 or pi 2 but a third policy, and we have to select the policy like that. So if I can visualize it, so our third policy should be something like this, right? Our third policy should be something like this: pi 3 optimal. Okay, so our goal is to find the optimal policy. So we have lots of our policy, but our quest is to find the optimal policy, and that is our optimal policy, the one given, right? So Cauchy, no, it's not so Cauchy. So your Bellman equation have there are some optimal versions of your Bellman equations which was given in the class. So your optimal Bellman equations will be something like this. Suppose pi star is the optimal policy. So your V star at S will be max. We will select the pi which gives max at S, right? Now can this be visualized by this graph, which I have drawn? Does this curve, does pi 3 represent this? Does pi 3 represent this? Yeah. So does pi 3 represent this? Yes. So pi 3 represent this. So that is the intuition I am trying to say that. So you have two different policy, but what you have to find out that for each policy at each state we will select the one which gives me the best value, right? So that is my goal at this point of time when we are trying to find the optimal policy. Okay, so so I don't want to write the entire equation again here. So I think you know that what will be the equation, that you substitute the value pi and it will be the max. That is that, nothing more. Right. So other than that, if you remember, Another equation I think I missed, but I will write it here. Let me write it there where I should have written it. So what is the relation between v pi and q pi? So what is the relation between v pi and q pi? So your v pi is basically summation of pi a given s into q pi s comma a. This basically gives your this is basically relation between your v pi and q pi, right? So what does this mean? That at for each action we select the one which gives you the maximum value, right? Nothing more, nothing fancy. So this gives you a relation between v pi s and q pi s. Now so after this so after this so if you substitute here you will get the one. So one thing was more shown is that, so this is not a deterministic way of finding which one is the best one, right? So you have to give a deterministic algorithms. It is very difficult. So given the number of equations you will have, if you have a set of whole policy, so it will be a exponential term to find out the particular policy which will give you the best solution at each state, right? So the method we found used, if you remember the proofs, I will not go into depth of the proofs. So proofs was there for your Cauchy sequence, your Bonach fixed point one, and your that constant mapping thing, contraction mapping function. So one of the key principles were there. So that I will give you a rough indication. So what was the key principle about it, behind it? I will give not I will not go into the details. So you came across these things, right? Cauchy sequence, Banach fixed point, and contraction, right? So I think it was very difficult to understand the whole process. So I believe like it was not easy to go through the entire formula and all, but the simple fundamental reason what we are trying to do here. So our goal was to find an optimal pi, right? Now your deterministic solutions, that solving of equations, will not give you that. It is very difficult to find out a optimistic value from like this. It is very difficult because it will be a set of equations will be very high. So you have to use these special theorems and all to find out the best action that you have to select at each time. Now, uh, so if you want to get behind the mathematics and all, so one resource I can say is very good resource from where you can read this was this. Let me paste the link. So this link you can find out the entire proof of how the Cauchy sequence, Banach fixed point, and contraction we are trying to build. But the main goal was in this case was to find the a particular value function or pi. So what was the like, if I give you a gist of what we achieved from this, we achieved is that by continuous applying the value function over an operator L such that L pi into V. So you will, so this is one equation you will find, right? So here V star is a, so if you repeatedly apply this over this, so you will get some kind of an optimal solution. So you will get a value v which satisfies this equation. So what is L pi and V pi? If I have to L star V star is basically this. So if you look at this equation, so this is your V, and this whole equation, if you see, this whole equation is basically a function over V, right? So here is your V pi and here is your V pi. So this whole V pi is basically a function over V pi, right? So your goal is to find out a pi which satisfy this equation, right? That's it. And for that we use these different tricks, this Cauchy sequence, Banach fixed point sequence, and contraction to find that value. That is the crux of the gist of the videos that there, nothing more. So one thing, like if you go through this part, um, so the link I have given there, you can find this in a much deeper knowledge, but not much is required. Okay, so let's now start this week's like we get to this week's assignments and all to solve it. So first of all, any doubt you can ask. If you have any doubt regarding this week's theorems and all, you can ask. Okay, so let's start solving the problems of this week. Let me open another. Let me just open another Jamboard. Okay, so let's go through this sum. Okay, so so uh, so this says that you receive a letter from your friend, and it says, so dear friend, sometimes ago I brought this. So if you have problem visible to see this, so you can directly go to the link and check it. Okay, so sometimes ago I brought this old house but found it to be haunted by ghostly sardonic laughter. As a result, it is hardly habitable. There is hope, however, for by actual testing I have found out that this haunting is subject to certain laws, obscure but infallible, and the laughter can be affected by the playing of an organ or burning incense. So, so the laughter can be affected by my playing the organ or burning incense. In each minute the laughter occurs or not, it shows no degree. In each minute the laughter occurs or not, it shows no degree. What it will do during this issuing minute depends in the following exact way on what has been happening during the presiding minute. So when there is laughter, so these are the conditions that are given. So when there is a laughter, it will continue in the succeeding minutes unless I play the organ, in which it will stop. But continuing to play the organ doesn't keep the house quiet. I notice, however, whenever I burn the incense when the house is quiet and do not play the organ, it remains quiet for the next minute. At this minute of writing, the laughter is going on. Please tell me what manipulation of incense and organ I should make to get the house quiet and to keep so. So it is given. So let's read the question properly first. Complete. So assume we make the following decisions in formulating the problem as MDP. So you have these states. So you are being said that formulate the problem as MDP. So you have a state set LQ, where L indicates there is a laughter in the room and Q indicates that the room is silent. So these are the two states you have. Then you have an action set where O represents playing the organ and I represent burning the incense. So these are a combination of four. These are all combination of all the four uh, action that can be possible. We consider this as a continuous discounted problem with gamma is equal to 0.9, and we let the reward be +1 when we transition into a silent state and -1 for any transition to the laughing state. So this is your laughing state and this is your silent state. So if we make a transition from here to here, you get a +1 reward. If you get a transition from here to here, you get a -1 reward. That one is same. And if it remains for any transition to laughing state, also think like this. So if you are in the laughing state and if you make a transition to the laughing state, it will also be -1 because it is a transition to the laughing state only, right? However, again similarly, if you make a transition to the quiet state like this, it will be +1. So assume a deterministic transition and reward based upon the current state and action. Which of the following four tuples represent the correct transition and rewards? Which of the following represent the current transition and reward? So basically, this is your state and action set, and you have been given some conditions here based on which you need to find out the MDP. So you have to construct an MDP for this. So the question is, which of the following four tuples are correct? Like following four tuples, like the four tuples means you have a current state, action, next state, and reward represent the correct state transition and reward. Okay, this is your question. So we will like to solve this one using an MDP. Okay, so let's start it. So you have been said that there is a laughing state and there is a quiet state. Okay, fine. And you have your set of actions. So you have two actions generally, like two items. One is your incense, another is your play, like burning the incense. So I is equals to burning the incense and O is playing the organ. So your action set are O and I, O and not I, not O and I, not O, not I. So what does this mean? So what are this action corresponds to? So the first one corresponds to that you are playing both the organ as well as lighting the incense, right? Burning the incense. This is your first action. Your second action is you are playing the organ but not burning the incense. Your third action is you are not playing the organ but burning the incense. And your fourth action is you are not burning the organ as well as not burning the incense. That is your uh, that is your all your states, all your action pairs. So now we need to find out the state table, right? So you have your current state, you have your action, you have your next state, and you have your reward. So let's consider the first one. Okay, so your current state is, let's say, in laughing state. Okay, so also note, any movement from here to here is +1, any movement from here to here is +1, any movement from here to here is -1, and any movement here to here is -1, given the definitions, right? Okay, so let's come to one of them, each of them one by one. So current state is L, action is O and I, next state is, let's say, so what does this mean? Current state is L, we are playing the organ as well as lighting the incense. So let's jump to this part. So what is this sorry, yeah. Okay, so this says when there is a laughter, it will continue in succeeding minutes unless I play the organ. So when they play the organ, so it jumps from this to this state. Okay, so it's playing the organ, so this action will be true. So the next state will be, so it's the current state is L, it's playing the organ, so the next state will be Q, it goes to the quiet state, and the reward will be +1, right? So this is the transition that is making. Now consider this one. You are in L state. You are in L state, and next you are doing this transaction. You are doing this, taking this action. Not of I. What? Not of I. So what will be the next state and the reward? What will be the next state and reward in this case? You are currently at L. You are burning the candle. You are playing the organ, but not lighting the incense. So what will be the state? So it is said that if you are playing the organ at laughing state, it will always go to the quiet state. So this will also make the transition to quiet state. Incense at laughing state doesn't matter. Incense at quiet state matters, right? So this will again be, the next state will be Q, and the reward will be +1. All of you agree with this? Okay, fine. Let's come to the next one. Current state is L, and you are not playing the laughter state, you are not playing the organ, but burning the candle, burning the incense, sorry. what it will be? What it will be? Why it will go to the Q state? It is not playing the. It is not playing. It is not playing the. So it is not playing the organ, not Q. See, it makes the jump whenever there is laughter. It will continue on the sets. When I play the, let me just use different color here. Unless I play the organ, in which case it will stop. So when it plays the organ, it will become quiet, right? So if he doesn't play the organ, it will not be quiet. And also look at this part. Continuing to play the organ doesn't keep the house quiet. So if you are at quiet state and you play the organ, it goes to the laughing state again. It again goes to the laughing state. Now also the last part is this. So however, when I burn the incense, when the house is quiet, so you are quiet and you are burning the incense, and also do not play the organ. So you are burning the incense as well as not playing the organ. That time it remains quiet for the next minute. So it will remain quiet for the next minute, right? So that is what it is meant to say. Right. So let's come back to this. So it is not playing the organ but is burning the incense. And laughing state, incense doesn't matter. Incense only matters in Q state. So the next state will be N only, and the reward in this case will be -1, because any transition to L will be -1. This part is clear? Okay, so let's do the complete one. So what will be this case? It is not playing the organ and not burning the incense. So it is not playing the organ and not burning the incense. What will be the next state? Come on, it is same. You are not at laughing state, only playing the organ matters. So in this case it is not playing the organ. What will be the next state? So it will remain at laughing state only, right? It will not go to the since only after playing the organ it takes it to the laughing state or the quiet state. So it is not doing it. So it will remain in the laughing state and the reward will be -1. Next, let's look at, you are at Q state and you are playing the organ as well as burning the incense. What state it will be? So I notice whenever I am burning incense, however that whenever I burn incense when the house is quiet and do not play the organ, it remains quiet for the next minute, right? So this means if you are burning the incense, that is I, and not O at Q, will remain you at Q, right? So that is the thing. So in our case we are playing the at quiet state we are playing the organ as well as burning the incense, but playing the organ is enough to send it back to the Q state. it will be back to the L state, that is laughter state, -1. Okay, so similarly, you are at quiet state, you perform this action. So you are playing the music and not burning the incense. Playing the music at quiet state will always lead you to laughter state. So again -1, then Q minus O and I, that is, you are burning the incense but not playing the organ. So that will keep you at Q state with +1. And the last one, let me write it here, Q uh, not O not I, that is not playing the organ as well as not lighting the incense. The next state will obviously be L, because that's it, because it is not playing the organ. So if you not play the organ for 1 second, it will always lead yourself to the laughing state, and the reward will always be -1 in laughing state. Right, these are all your transitions. These are all your transitions. So which of the transitions are correct? So these are all your transition given. So you look at this one. So we'll go through one of them one by one and check if it is correct or not. Okay. So the first one is L, O and I. What is L, O and I? Next state is Q and reward is +1. What it is given here? Next state it is Q and the reward is +1. Right. So this one is correct. Next, we will check at L, O and not I. So you are at state L. You are playing the organ as well as burning the incense. Not burning the incense. What will be the next state in that case? In that case, the next state is Q, right? So the next state is Q and the reward is +1. And what is there in this case? Next state is L and -1. So this one is wrong. So B is wrong. Next state. Next we look at option C. L and the action is not O and I. Action L, not O, non I. So this one we are talking about not O and I. So the next state is L and the reward is -1. Next state L, reward -1. So here what it is, next L Q, reward +1. So this one is wrong. Right. Now let's consider the number D. Next current state is L. Action is not O and not L. Action is not O, not I. Okay, so this one is one talking about, and the next state is L and the reward is -1. So let's come here. Next state is L and reward is -1. Correct. Next look at state Q, O and I. Okay, let's look at state Q, O and I. State Q, O and I, L -1. The answer is L -1, and let's check if it is correct or not. Here Q +1. Sorry, so this one is wrong. This one is wrong. Next look at this one, Q, O and not I. Q, O and not I. What it is? Q, O and not I is L -1. Let's see if it is L -1 here. So it is L -1. So this one is correct. Next you have Q, comma, current state is Q. Action is not O and I. Not O and I. Action is not O and I. Next state is Q +1. Let's see it is even there or not. Yes, it is Q +1. So G is correct. Next come to option H, Q, not of O and not of I. And what is the state here? Not of O, not of I, L minus 1. So it will be L minus 1 and it is correct. So the correct answer is A, B, now A, D, F, G, H. Okay. So any doubt regarding the entire NDP formulation and all? So this is basically your state transition diagrams and all, nothing more. Nothing much fancy, but your state transition diagrams. Yeah. So, in the book, you will find these can picking theorem, can picking programs, and all those you can practice and get a hold of this one. So, how to do it and all. So, this is nothing like high above the plate and all, but this is very basic way to solve this. Very basic questions. Okay, so let's move to the next one. So, based on the above description, what advice you will give to mixed ignorance? So, you have been given. So you have been given. So based on the transition diagrams and all, you have been given. You have got this whole package. You have got this test transition diagram. So you have got this test transition diagram. So you have got this test transition diagram, and what all can you? What all you can? What is the best policy you can find out? So give advice is basically. So give advice is basically find the best policy, right? Find the best policy, which we turn can describe it as find the policy which maximize V. Right. Now, given this state transition diagram, how can you construct a simple simple proposition to help him get rid of these ghosts and all? No, quiet is not. You cannot give your just state. You have to give your you have to give an state action reward complete loop. How to do it? So you have to give you a state action pair and all. So our target is to maximize reward. Okay, fine. Our target is to maximize reward. So that is get more rewards, and more rewards you will get by transition to state queue. So so we are going to select. Sorry. So you are going to select this policy this policy and this policy, which gives us maximum rewards. So this value action pair, this right. So our target will be, so our target will be so our target will be in laughter state, number 1 t1 at time step t1. In laughter state, play the organ. Next, so here it goes to quiet state. At quiet state, burn the at quiet state, burn the incense and don't play the organ. Right. So that should be our policy. PRTLAQ. PRTLAQ, what does it mean? Here the policy is to keep the max quiet time. Yes, the policy's max quiet time is correct, but the policy's main target is to maximize the reward. So that you will get by more and more transition into the quiet state. And how are you going to make more transition into the quiet state? First, you need to make a move from laughing state to incense state, like laughing state to quiet state. That can only be possible through your uh, playing the playing the organ for one timestamp, and from the next timestamp you repeatedly just you repeatedly keep quiet and just burn the incense, and that is how you get the optimal policy. So the rewards will be 1 plus 1 plus dot 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 dot. Right. So any doubt regarding this? Yeah, fine. So the correct answer is option D. If there is a laughter, play the organ. If the room is quiet, do not play the organ and burn the incense. That is your optimal policy you can find to get out of to get the maximum reward. Okay. So let's continue and go to the next one. Okay. So if a policy is greedy with respect to its own value function, then it is the optimal policy. Is this statement true or false? So the so let's again draw this diagram. So this is your value and this is your time space, right? This is one policy, this one is your other policy. So let's name this pi 2 and pi 1. Now if a policy is greedy with respect to its own value function, then it is an optimal policy, the term says. So what is the optimal policy in this case? So in optimal policy in this case will be something like this, right? So up to this it will follow pi 2, and from this to this it will follow pi 1. So so it is basically greedy. So you say it always selects the one which is better. Why false? Our this algorithm is quite completely greedy. It always tries to find the max one. Now the value, the state, the value, max value at each state. It's just entire job is to find the max value at each state, nothing more. So the poly is greedy. Yeah. So yeah. So there are, these are all its own value functions. So these are all. So if you are given a pi uh, set of policies, set of policies like pi 1, pi 2, dot dot dot, pi s or pi star, goal is to uh, given any value function, given any value function, always select the max at each time, right? So from that concept, yeah, optimal policy is basically chosen from a set of policies, right? Optimal policy is so if you remember, if you remember the derivations, so we are talking about a vector space of V, right? Vector space of V, and 1 minus 1 by R, something like this was there, right? How can it be specific to its own value function? I mean, if you think about it, in a vector space is basically this whole jumbled up, consisting of all the values, right? So value functions, right? So at each step, its determination is to be greedy with respect to the value function, the policy. So this statement's main objective. So if you are confusing it, so the statement's main objective is to say that, okay, so at each time step I set the maximum value. Pi 3 is decreasing initially and then increasing. Yeah, but pi 3 is always at the top of its game in case of its of other of its rivals like pi 1 and pi 2. Increasing and decreasing, it's not a factor. So uh, it's just it's just uh, like ambition is to find the max one at each state, nothing more. No, how can greedy that it did not move to a lower value? Greedy means selecting the value at the highest one. So in that case, in this state, in this state, in suppose in this state, right? So this one is the highest value. So it is taking this value, right? That is greedy, selecting the highest value. In this state, this one is the highest value. So it will state that value. So that is greedy. Greedy doesn't mean not moving to a lower value. Greedy algorithm can go fetch for negative values also, right? Okay, so let's move to the next one. So you have been given, so consider 4 cross 4 grid problem, 4 cross 4 grid problem, where the goal is to reach either the top left corner or the bottom right corner. So this is a 4 cross 4 grid problem. So here is your grid. So the goal is to either reach the top left corner or the bottom left corner. So its own value function is basically the maximum of everything, right? So its own value, it doesn't have its own something that big value function. So its value function is selecting. So its value function is selecting this. So this is its value function. So at each case, it is selecting the maximum of its subordinates, right? So that's its own value function. That's what it means, nothing more. So at each state, it is selecting its own value function, selecting the one which is giving it the maximum value, nothing more. That is its value function. So these means greedy. Okay, so if you have any doubt, you can ask me later after the class. Okay, so let's come to this one. So you have a 4 cross 4 grid, and your goal is to reach either the top left and the top left corner or the bottom right corner. The agent can choose 4 actions: up, down, left, or right. Right. Which deterministically cause the corresponding state function, except the actions would take the agent of the grid and leaves unchanged. Uh, so these are the 4 actions it can take. So each action, so each except the action that would take the agent of the grid. Okay, we don't have to consider that part. So some actions with, that means to say, if I want to go in the top here, that will take me out of the grid. So that one we will not consider. That will not. So if mm, if so suppose if it is like this, so if the problem is like, suppose if I am here, so if I am at state S and I order move up, so this will be a circular loop, so it will come back to that state only. When I set up, it will come back to that state only, right? So that is what it means. And so reward for all transition is -1. For all transition, the reward is -1. Suppose the agent follows equiprobable random policy. Given the partial value function of this problem, calculate the missing values in first and second row. We have to find this one and this one, right? The value functions in this one and this one. Now let's do this. So let me just read out this here. Zero minus 20 minus 22. 0 minus 20 minus 22 minus 14 minus 18 minus 20 minus 14 minus 8 minus 18 minus 20 minus 20 minus 18 minus 14 minus 18 minus 14. Okay, so this will be enough. Okay, if I will write the last row also. Minus 22 minus 10 22 minus 20 0. Okay, so we have to y, so this let me write it as v1 v2. So we have to find v1 and v2. So let's write the equation for v1. Summation pi a given s summation is dash comma r p of is dash r given is comma a r plus gamma v1 is dash, right? So this is how you can write it. Okay, now the problem also says that it is undiscounted. So it says that it is undiscounted. So it is saying that the problem is undiscounted, right? So if it says it is undiscounted, that means gamma is equals to 0. So this will come down to, so this gamma value will substitute as 0. So this is come down to summation a given s given s dash comma r p of s dash r comma s comma a r, right? Now check one thing. For each of this state and each of these actions, so for this state there are 4 actions, right? For each for this state there are 4 actions: up, left, right, down, right? For each of these action there is only one state, there are not more than one state, right? Check. Right, for each of them there is only one state. For each action there is only one state, right? There are not multiple states. So what it will be? So this will be 1, right? Because it is deterministic, it is constant, it doesn't change. And so this one will become, so what does this mean? So this means given, so this probability, what it means, given state A and action, state A and action A, probability that next state is dash and reward R, right? But you see here we have fixed values of rewards and everything. So suppose we are taking a left turn. For this grade we are going left. For if the action is left, there is only one reward and the state is only one, right? So it is deterministic, it is not there are multiple states for going left, right? For going left there is only one state and one reward, so this part we will consider as 1. So this probability will tends to 1, right? There is only one state, so it will ultimately come down to summation of A pi S into R, right? Now one more thing is said, that each of the actions have equal probability of happening. Going left, right and center have equal probability of happening. So this one will be 1 by 4. There are 4 events, probability 1 by 4. So this will be 1 by 4 into what are the rewards. So either it can go to the left, right, top and down. Okay, so if it is going left, what will be the reward? 0, and there is constant -1, plus if it goes right, what will be the reward? 20, -20, -1, plus if it goes to the bottom, what will be the reward? -18, -1, plus if it goes top, it will come back to the same place. So it will be V1 -1. So this will come down to, so if you add this up, one -22, -22, -1, -20, -21, -22, 40, 41, 42. So it will be V1 equals to 1 by 4 V1 minus 42, right? So if we solve this, V1 is equal to 1 by 4 V1 minus 42. So that will be 4 V1 minus 42, or 3 V1 minus 42, or V1 is minus 14, right? So the value of V1, so value of V1 here will be minus 14, correct? So we can come back here and we can write this as minus 14, right? So now we have to find this one. Again we will do the same thing. Again this part will remain same. So I mean to say this part of the equations will remain same. So ultimately we will write it now from here, right? So it will be V2 is equals to 1 by 4. Let's add all them up. V2 is equal to 1 by 4 minus 22 minus 1 minus 22 minus 1 plus this one minus 20 minus 22 minus 1 minus 20 minus 1 minus 20 minus 1 plus minus 14 minus 1 plus V2 minus 1, because the state transition if it goes to the right will come back to the same state, that is the state. So let's solve it. V2 is equals to 4 V2 is equals to V2 minus 23 43 44 58 let me do it again. 22 minus 1 23 22 minus 10 minus 14, right? 22 minus 20 minus 14. Okay, sorry. So this will be minus 23 44 minus 23 minus 43 minus 44 minus 49 minus 48 minus 59 minus 58 minus 59 minus 60, or 3v2 is equal to minus 60, or v2 is equals to minus 20, right? So this value, so this value will come down to minus 20. So the correct answer is option B, minus 14 minus 20. Okay, so let me share this tab again. So this calculation is basically substituting the values and solving it. So main trick lies here. So gamma is said to be 0, that is one thing. That part, so this part becomes 0. The other trick remains here. Since for each state, the next state there is only one state, for each action there is only one state and only one reward, so this part will become 1, because there is one probability. So if you are given a coin which always just tosses to whose both sides are your heads, right? So in that kind of situation you can think about, right? And then you substitute the values and just solve the equation, and this is the two values you are getting. V1 equals to 14 and V2 equals to minus 20. So any doubt regarding this? You can just solve the equations and you find the answer. Okay, so let's go to the next one. So now they are saying that the grid is same. So if pi is equiprobable policy, if the pi is a equiprobable policy, what are the respective q pi s1 down and q pi s2 down, where s1 is the last cell in the third row. So they are saying this one is s1 and s2 is the last cell in the second row. So this one last cell in the second row, this is s2. So both case you are saying what is the value by going down we are getting. So what is the value we are going down by getting? So we have to find q pi is 1 down. So what it will be? So we have to look at the q function. So let's look at the q function. Q of s dash comma r by s comma a r plus gamma v pi s dash. Again gamma is 0, so ultimately this becomes only this part, summation of s dash r q of s dash minus r s of a into r. Now again the same fundamentals, that since you are going down, so there is from so we are doing s1, so this part, so we are going down, there is only one option down there, so there is no other actions can be associated with this. So this problem, there is only one part, so only this to this, so this will tends to 1. So this will be basically sum of the rewards. So which will basically be your this one 0 minus 1, the reward you are getting, so that is minus 1. Okay, so similarly q pi is 2 comma down, so it's coming from here to here, will be basically minus 14 minus 1, that is minus 15, right? So the correct answer is option A, minus 1 minus 15, right? So any doubt regarding this? So basically you need to calculate the movements from, yeah. So it might seem easy to do it without recognizing anything extra, like okay, we don't have to go to the formula and all, but this will give you an idea how to apply the value functions in normal cases, in maximum cases, to find out. Okay, so let's go to the next problem. So in a particular grid wall problem, so in a particular grid wall problem, rewards are positive for the goals, negative for running into the edge of the world, and zero rest of the time. Are the signs of this reward important or only the interval between them? So our question is, are these signs important? So suppose we change these signs. So for goals we are giving negative, for running into the edge of the world we are giving positive, and so on. So we don't have to think about it. So our question is, prove that for a discounted return equation, for the discount for using the discounted return equation, that adding a constant pi to all the rewards adds a constant k to all these states, and that doesn't affect the relative value in any in any policy, that is k is equals to k is 1 in terms of c and pi. Okay, so what they are saying is, in this reward we are adding an extra time constant c. Okay, so we are adding a constant c, and how does it affect it? How do you set gamma to 0? Did I set gamma to 0 or gamma to 1? One minute. Sorry. So this gamma will be 1. Sorry. Undiscounted is gamma is equals to 1. So this gamma value will be 1. Sorry. So this one will become r plus v pi. So this gamma value will be 1. And rest of the equations will be same, because this reward is minus 1 and the value function is 0. Value function at state s dash is 0, 20, 20, 18 and all. Okay, the rest of the calculations will be same, but it will be that the value functions value we are adding. Similarly in question, these two also, this also same. This will be this will be 1. So if it goes to 1, it will ultimately become this. R plus v pi is dash. So the reward is minus 1 and v pi is minus 14, equal to minus 15. And similarly here, sorry, in this case from 0 to 1 is 0. It is 0. Minus 1, and similarly here. Now it's okay, right? Yeah. Okay, so let's do this one. So what we are saying here, we are adding a constant term to the reward. We are adding a constant term to the reward. For each reward we are adding a constant term. So this gt can be written as summation k equals to 0 to infinity y to the power of k rt plus k plus 1 plus c. This is what we meant by adding a constant c. Okay, so now we will find the expectation of this, right? We need to find the expectation of this. Expectation of, so this will be the value function. V pi is equals to expectation of gt given st is equals to s, which will be, so sorry, let call this gq. Okay, so let's call this gq, not gq, gt dash, sorry, let's call this g t dash, g dash t, g dash t. Okay, so now what we can do is we can write the expectation as gamma k r t plus k plus 1 plus c. And what we can do is we can just we can just rearrange it. So we can just use the expectations, the sum property of the expectation, and do it like this. E is equals to summation 0 to 0 to infinity alpha k r k plus t plus k plus 1 plus c. Right, now we are using the chain rule to do this. Summation 0 to infinity y to the power of k r t plus k plus 1 plus expectation summation 0 to infinity c given, yeah, so the st is equals to s, this one will remain, st equals to s, right? Now this one is basically your, so if we are considering this v pi star s, so this one is your v pi s, right? V pi s only the formula. And now you have to calculate this this expectation of this constant c. So if we do this, it will come down to, so this is basically a infinite series, right? Infinite series over okay, so this part is there, y to the power of k, so we take the c out and do a summation of y to the power of k to the power of infinity. So this will be 1 by s plus c k divided by 1 by 1 minus gamma, right? Infinite series is sum of 0 to infinity a k is equals to 0 to infinity a k is basically 1 by 1 minus a, right? So that comes here. So this is your constant which you are getting k value, right? So this is the k value you are adding, uh, corresponding to this. Why is k added to t, and why is k added to t and becomes a subscript of r? Why is k added to t? Is k added to t? Which k? Small k or capital K? Small k or capital K? Capital K. Oh, the we are not adding it to t, right? It comes out like this, right? If we do this, like expectation calculation, it will come out to be like this. I am not saying we are not adding k. We are adding basically a constant. This constant. So what we are trying to say is that if we are adding a constant to a reward, so there is an extra constant value that will appear, corresponding to the v pi, which in turn it means, which what it turns and means that the what the previous values were there. So previous values were your v pi, and new value is v star pi. So it becomes relatively same, only this small term is added. So if we do a minus like v pi, what I mean is this. So suppose what I mean is this. Suppose there were previously policy ps1 pi ps. Suppose this is a subtraction we are doing, ps1 minus ps2. This will have some value, right? Now in this new policy, p dash s1 minus pi dash s1 s2 remains the same, right? This will remain same, right? Because we are just adding this constant to the reward. So this relativity remains same. That is what we are trying to prove. Understood? Yeah. So if you look at the question, it says that. So does not affect the relative values of any state. So relatively these are same under any policy. So we are just adding a constant term, nothing more. So that is your this. Okay. So so this is the last question. Let's do this. So given a reinforcement learning problem. So given a reinforcement learning problem, with algorithm A, we'll return the optimal state value function for that problem. So we have a problem A and we have a value function pi for each state. So algorithm A will give us this v pi A, algorithm A. Algo B will give us q pi s comma A, right? Our aim, the aim is to use the value function so obtained to behave optimally in an environment, assuming that you know the expected rewards and but the not the transition probabilities corresponding to the problems in the question. Which algorithm would you prefer to control the task? So you have been given this and this. Which one will you choose for this algorithm? Which algorithm will you choose to find an optimal result for p? Which one will you choose? Why A? A requires a certain specific thing which you don't have. What does A require? A requires this transition probability. So suppose you are at state S. So and there are three states you can go: S1, S2, and S3. How do you know which was to? You have this value for this algo 1. You have this value at this position, but how you don't have values for the. So you don't know which one will give you the most, right? You know this value, but you don't know which state to go. You don't have the transition probability. So that's why algo B is better, because For state S, you know which function, which for each action, suppose this is action A, B, and C, you know action value A will give you how much value, action B will give you how much value, and action C will give you how much value, right? So, that's the reason you will select algo B, because you will just probe one by one, and you select the one action which gives you the maximum value, nothing more. Okay, so algorithm B is the correct answer. Okay, so that's it for today. So if you have any doubt, you can ask now. And thank you for joining. We'll again meet next week. Okay, thank you.